Okay, in chapter 5, we're going to look at eigenvalues and eigenvectors. Eigenvalues and eigenvectors are an inherent property of matrices, okay, and vector spaces and the like. Okay, one of our many things that we're looking at here to develop our tools that we can use, figure out independence, different relationships with linear transformations, etc. Now, eigenvector and eigenvalue is a strange kind of word. So the question comes up, where does eigen come from? Okay, well, eigen is German for own. Okay, you notice I have proper values marked out there. We also used to use the term proper values. When I say we used to, I don't mean me. That's going way back in the history of mathematics when they would use that term. But own as in something that's inherent to the matrix, okay? Something that's a property of the matrix or the transformation, okay? It's belonging to, it's important, it's ingrained in, okay? It's something that is that matrix, okay? It helps define what that matrix is, what that matrix does, or what that transformation does. So that's why we call it an eigenvalue or an eigenvector. Okay, so let's look at a matrix and let's look at some things that happen to it. So I have a matrix here, A, okay, 4, 1 on the top row, 0, negative 3 on the bottom row. U is going to be 1, negative 7. V is going to be 2, 1. Okay, and I want to look at what happens if I multiply. So I take A times U. Okay, so I do A times U. Okay, so again, we're multiplying across here. So 4 times 1 is 4. Negative 7 times 1 is negative 7. Add those together, I get negative 3. 0 times 1 is 0. Negative 3 times negative 7 is a positive 21. So negative 3 and 21. Now notice that that vector is exactly negative 3 times the vector I started with, 1, negative 7. So if I do negative 3 times u, I get exactly a multiple when I do a times u. Okay? So we're going to call this negative 3 value here, we're going to call it lambda. That's a Greek letter, okay? You write it with the two pen strokes. You go up and over, and then you come out the back side, sort of like a K, okay? But maybe a backwards K of sorts. So up and over, and then back, okay? Slash back. You'll see me write a few more as we go through here, okay? But maybe you're thinking, well, maybe that's something to do with this matrix, that this happens for any vector in this matrix. Okay, let's look at A times V. Okay, so notice A times V, okay, again, multiplying across and down, right? So 2 times 4 is 8, plus 1 is 9, 0 times 2 is 0, minus 3 is negative 3. Notice that 9, negative 3 is not a multiple of V. There's no value here for lambda that I can multiply and get 9, negative 3, okay? So this is going to be an important relationship. When I have a matrix that when I multiply it by a particular vector, I just get a multiple of that vector. Okay, in this case, lambda equals a negative 3. Okay, so let's define then what this is going to mean for us for an eigenvalue and an eigenvector. Okay, so we have a bit of a long definition here. Okay, I'm going to put the whole thing up here and read and talk about it. Please take your time, use pause on the video if you need to. Make sure you're getting the whole picture here. Okay, so an eigenvector, okay, there's that definition, an eigenvector of an n by n matrix. So notice it's n by n, it's specifically a square matrix. Okay, so we do not talk about eigenvectors or eigenvalues of non-square matrices. We're only looking at square matrices. Okay, so an eigenvector of an n by n matrix, A, is a non-zero vector x such that ax is equal to lambda x. Okay, lambda is spelled L-A-M-D-A if you want to know how it's pronounced, but it's the Greek letter lambda, just like alpha, omega, beta, so forth. It's just another one of those Greek letters called lambda. Okay, so we have a non-zero vector. Notice that's important, non-zero vector x such that ax is equal to lambda x, and lambda is a real number. Okay, now we can talk about complex eigenvalues. That is not going to be a big focus. We will touch a little bit on them later in the chapter, but for the most part, we do not really work on complex eigenvalues. Okay, we're really only looking at real eigenvalues. Okay, so consider real eigenvalues. Lambda is a real number. Okay. Then we also have the corresponding definition here with eigenvalue. The scalar lambda is called an eigenvalue of A if there is a non-trivial x that is a solution to ax equals lambda x. So notice it's a non-trivial. That's why I've written that arrow coming off a non-trivial. That again means that x is not 0, okay? Now notice in this definition, we have not said that lambda can't be 0. So lambda can be 0, it's a real number, but x cannot be the 0 vector, okay? So I've tried to bold that there. It cannot be the 0 vector, okay? So non-trivial, so that should invoke some ideas about systems of equations for you, okay? Non-trivial. We need a non-trivial solution, so a non-zero solution to ax equals lambda x. So those are definitions for eigenvalues and eigenvectors, okay? So let's look at another matrix here and see if we can start getting a feel for what happens here with these eigenvalues and eigenvectors. So I'm going to have a matrix A. That matrix A is 3, -2 on the top row, 1, 0 on the second row. Okay, U is going to be equal to -1, 1, and the vector V is going to be 2, 1. Okay? So let's multiply. So A times U, okay, 3 times a -1 and 1 times a -2. Put those together, I get -5. -1 times 1 is a -1 plus 0 is a -1, okay? Notice that is not a multiple of U. There's nothing I can multiply U by to get this vector, okay? But V, on the other hand, 2 times 3 is 6, minus 2 is 4, and 2 plus 0 is 2. So I get 4, 2. Notice that is 2 times V. If I do 2 times 2, 1, I get 4, 2, okay? So 2 is going to be an eigenvalue of this matrix. Okay, so 2 is an eigenvalue of A, the matrix, and 2, 1 is an eigenvector of A, but these correspond. So the eigenvalue goes with an eigenvector. Okay, this eigenvalue goes with this eigenvector, and this eigenvector goes with this eigenvalue. Okay, they're a pair. You have to have that pair. Okay, now you can have an eigenvalue with more than one eigenvector. Okay, but you have to have a pair. You can't have an eigenvalue and say, oh, it's an eigenvalue, but I don't know the eigenvector. Well, you can find the eigenvector. You can't have an eigenvector and say, oh, I'm not sure what an eigenvalue would be. You've got to have that paired relationship, okay? Now, we also want to think about this visually. So if I have the vector u, again, -1, 1, you can see that vector u. The vector au is -5, -1, so that's coming out here. The vector v is 2, 1. And the vector AV is 4, 2. So notice that that is on the same line, V and AV. Okay? So we're looking at these particular vectors that have this relationship where they extend along that same line because of the matrix. All the matrix does is it keeps it in line. It just makes it bigger or smaller. Okay? It just makes it a multiple. You can have fractional eigenvalues. Nothing we said couldn't be a fraction. Okay? But we have this equation, AX equals lambda x. And we want to look at the implications of that equation. So I have an equation. So I can take lambda x in this equation and move it to the left-hand side. Okay, and so I will have ax minus lambda x. Well, I have vectors and matrices, so I can do factoring. I can do distribution, right? I can factor that x to the right, okay? So it would be distributed on the right, okay? And this would be a minus lambda, but I can't really do a minus a constant. This lambda should be a matrix, so it's lambda times the identity equals 0. And this we should recognize is a matrix equation. And we know how to solve matrix equations. We know how to determine the solutions, okay? We've written solution sets in each of chapters 1, 2, and 4. Chapter 3 just dealt with determinants, so we didn't talk about them there. But chapters 1, 2, and 4, we talked about solution sets in each of those chapters. We've been writing solution sets, whether it's for a vector space, a system of equations, a matrix equation, a vector equation, etc. We have all of those tools. So we're going to be writing those solution sets and using those solution sets to help us with our eigenvalues and eigenvectors. Okay, so let's look at a couple more examples here so we start getting a feel for what is happening when we have an eigenvalue or an eigenvector. Okay, so I'm going to have a matrix A. Get it in the picture there for you. I've got a matrix A, and this matrix A is 1, -1, 6, -4. And I want to know, is the vector 1, 3 an eigenvector of A? Okay, so I know to be an eigenvector, I need it to satisfy ax equals lambda x. Okay, so let's multiply a times x. Okay, for us, that's going to be this matrix times the vector 1, 3. Okay, so let's multiply. 1 times 1 is 1. Negative, I'm sorry, 1 times 1 is 1, and then I'm going to subtract 3 from it, so I'm going to get a negative 2. And then the second row, I've got 6 minus 12, that's a negative 6. Okay? So notice that the top coordinate is multiplied by negative 2, and the bottom coordinate is also multiplied by negative 2. Okay, so this relationship then is negative 2 times x. Okay, so what this tells us is that lambda is equal to negative 2 for eigenvector 1, 3. Okay, so I do have an eigenvector there. So yes, this is an eigenvector. Its eigenvalue is negative 2. Okay, now we know this is an eigenvector, so we should get a relationship here that we can look at. We know that I'm looking at a minus lambda I times x is equal to 0. Okay, I know this is going to work for lambda equals negative 2. So I'm looking for a plus 2I times x equals 0. Okay, minus 2, and then it's minus here inside the equation. So minus and minus is going to make this plus. Okay, so a is 1, negative 1, 6, negative 4. I'm going to add 2 times the identity. So remember, the identity just has 1s on the diagonal, but I'm multiplying those 1s by 2. And then it's times x, again, the vector x, and equal to the 0 vector. So let's add these components of this matrix. I get 1 plus 2 is 3. Okay, I get negative 1 still. 6 and 0 is 6. Negative 4 plus 2 is a negative 2. Okay, and this is times x equals 0. So notice then I would write this with an augmented matrix, right? This would be 3, 6, negative 1, negative 2. Augment that with 0. Okay, and notice that the columns are multiples of each other, right? I've divided this by 3 to get here. I divide that by 3 to get there. So if I row reduce this matrix, okay, use your row operations if you like. Go in, type it in the calculator, whatever works for you to row reduce that matrix. Okay, and what I get is I get 1 and negative 1/3 with zeros on the bottom row. Okay, and so I would write a solution set to this matrix. This would be x1 is equal to 1/3 x2, or x2 is equal to x2. And I should say, not or. Okay, that would be my solution set. So pick a value for x2. So frequently we pick 1. 1 is a fine value. Okay, I would get a vector here. This would be 1/3 1 if I picked 1. Maybe I want to pick 3. Okay, maybe I want to pick 3 so that it will cancel this fraction. So I will get 3 for x2, but I'll get 1 for x1 because it'll be 1/3 times 1. 1/3 times 3, I'm sorry, will give me 1. And notice 1, 3 is my eigenvector. Okay, so my solution set here told me what my eigenvector was. So what we're going to do to find eigenvectors is we're going to take a minus lambda I, okay, and we are going to augment this with the 0 vector, and we're going to row reduce this, and we're going to find non-trivial solutions. And if I find a non-trivial solution, those non-trivial solutions are my eigenvectors. And the lambda that I use to find a minus lambda I is going to be my eigenvalue. Okay, so we're going to have both of those tools in our toolbox. Okay, so let's expand our repertoire here to a 3 by 3 matrix. So I'm going to have a matrix A. And this matrix A is going to be negative 4, 3, 3, 2, negative 3, negative 2, 1, 0, negative 2. And I want to know, is the vector 3, negative 2, 1 an eigenvector of A? So what do? I do A times X. So AX. Okay, I'm going across, so I got negative 12 minus 6 is a negative 18 plus 3 is a negative 15. Okay, so it's negative 12 minus 6, negative 18 plus 3, negative 15. Second row, I've got 6 minus 6 is negative 12. Minus 2 is negative 14, right? 6 minus 6. Oh, I'm sorry, I said that backwards. 6 minus 6 plus 6 is a positive 12. There we go. Minus 2 is a positive 10. Okay, so we had 6 plus 6 was 12, minus 2 is a positive 10. Bottom row, 3 plus 0 is 3, minus 2, 3 plus 0 minus 2, that is going to be 1. 3 plus 0 minus 2 is 1. Okay, so I was looking good here on the first two, right? This was 3 times a negative 5 gave me negative 15. Negative 2 times negative 5 is a positive 10. That looks good, but then this third row, 1 times a negative 5 is not that. So there is no value of lambda that will solve this, that will make this work out. Okay, now all that means is this isn't an eigenvector. That does not mean that it can't have an eigenvalue. Okay, that's just one that we've been able to cross off. Okay, so we'll look back at this. We can look back at this matrix later. Okay, maybe the next section, or you can, once you know more, you can go back to this matrix and see if you can determine its eigenvalues and eigenvectors. But for now, right, the question just says, is this an eigenvector? No, not an eigenvector. Okay, so let's try another one. Let's call this one B. Okay, B is going to be 3, 6, 7, 3, 2, 7, 5, 6, 4. And my vector X is going to be 1, negative 2, 2. Okay, so let's compute Bx. Same question. I'm not going to write out the question again, but same question. So I get 3 minus 12 is a negative 9 plus 14. That makes 5. Second row, I've got 3 minus 4 is a negative 1 plus 14. So I've got 3 minus 4, negative 1, plus 14 is 13. And then I've got 5 minus 12 is a negative 7, plus 8, that's 15. Okay, clearly this doesn't work either, right? There's not anything I can multiply that to make that work out right. Okay, now still may have eigenvalues and eigenvectors. Okay, in fact, there's a very good chance it does. It's pretty much guaranteed, but it's not that one. Okay, so we can look at plenty of others and try to deduce their eigenvalues, eigenvectors, etc. Okay. All right, so at this point, I've given you vectors and said, are they eigenvectors? Okay, well, we also want to look at it the other way. What if I give you a matrix and say, is this an eigenvalue? Okay, so I'm going to have a matrix A, and my matrix A is going to be 1, 6, 5, 2. Okay, so is lambda equals 1, negative 4, or positive 4 an eigenvalue for A? Okay, and if it is an eigenvalue, we want to find its eigenvectors. Okay, so we said to be an eigenvalue, I have to have non-trivial solutions to ax minus lambda x equals 0, which we also wrote as a minus lambda I times x is equal 0. Okay, so I have my candidates here. So first, let's do a minus, in this case, just I, 1 times I. So I'm subtracting 1 on the diagonal. So 1 minus 1 is 0. 0 minus 6. 6 minus 0 is 6. 5 minus 0 is 5. And then 2 minus 1 is 1. Okay. So as I look at this matrix, these two columns are clearly independent. And if those two columns are independent, I know they reduce to there. Okay. And if they're independent and they're reduced to there, I don't have any non-trivial solutions. I don't have any free variables. So no non-trivial solutions. Okay. 1 is not an eigenvalue. Because remember, we need non-trivial solutions in order for it to be an eigenvalue or an eigenvector. And this equation, this matrix, clearly does not have that situation. Okay, so let's go to the next one. A plus 4i. Remember, it's a minus lambda I, but lambda here is a negative. Okay, so let's go. We're going to add 4 on the diagonal. So I'm going to have 5. 2 plus 4 is going to be 6. 6 and 5 are unchanged from the original matrix. Now this I can do row operations on and reduce, right? This is going to row reduce. You know, I could divide, for example, I would get 5, 6, 0, 0 first, right? I just do negative row 1 plus row 2 is going to replace row 2. And then I'm going to take row 1 and divide it by 5. So it's going to finish out at 1 6/5 with 0 and 0. So I could write the solution set. So x1 would be negative 6/5 x2, and x2 would be free, so just x2. But perhaps I want to kill off the fraction, so let's make a vector that's going to have 5 down here, so it'll kill the fraction when I put it in. When I put 5 in there, I'm going to get negative 6 in the numerator. Okay, so negative 6, 5. Let's check our work, okay? If I do A, which remember is 1, 6, 5, 2, times my vector I just found, negative 6, 5. And I multiply those. So I've got negative 6 plus 30. That's a negative 24. I've got negative 30 plus 10. It's a negative 20. Sorry, I think I said the first one wrong, right? So I've got negative 6 plus 30. That's a positive 24. Sorry about that. I was thinking ahead to the negative 20 on the bottom one and got it crossed up my mind, right? So negative 6 plus 30 is going to be a positive 24. And notice that this is exactly negative 4 times the vector I found over here. Let's call this vector u. So this is negative 4 times u. Okay, perfect. We confirmed that that is an eigenvector and that negative 4 is an eigenvalue. Okay, so eigenvalue 4, so lambda equals 4 with u equal to negative 6, 5. Okay, that's the eigenvalue and the corresponding eigenvector. Okay. Now, if you think back to what the visual of an eigenvector looked like, right? It was this multiplication. Well, this looks like the span of vector v. Okay, so for that reason, we call the eigenvectors an eigenspace. Okay, when I say positive 4, that should be negative 4. I wrote negative 4 over here. It's lambda is negative 4 in this example. We have an eigenspace, and the eigenspace here is going to be E with the little sub negative 4. So we're writing the eigenvalue that it corresponds to, and that eigenspace is equal to the span of all the eigenvectors. Okay. Now, if you're thinking about this setup, the most eigenvectors I can find is possibly 2. Okay, because each time I am finding I can only have up to that many free variables. Okay, I can't have more than 2 free variables here. I only have 2 variables. And each eigenvector has to correspond to one of those free variables. Okay, so the most eigenvectors you can have is the number of variables in your original system, your original matrix. Okay, all right, so let's check our last one. A minus 4i in this case. Okay, so again, I'm taking A and I'm subtracting 4 on the diagonal. So I'm going to get 1 minus 4 is a negative 3. 6 and 5 stay the same. And then 2 minus 4 is a negative 2. Okay, again, notice these are not multiples of each other. Okay, so I can already say that that's going to reduce to there. So I get the same conclusion. No, 4 is not an eigenvalue. Okay, because I have no free variables in A minus 4i equals 0. Okay? All right, so let's expand to a 3 by 3 matrix. Okay, so I've got a 3 by 3 matrix here. We'll call it B. B is 4, negative 1, 6, 2, 1, 6, and 2, negative 1, 8 for the third row. Okay, and so the question is, what about lambda equals 2? Okay, well, if I'm going to research lambda equals 2 here, I'm going to need B minus 2i. Okay, which means I'm subtracting 2 from the numbers on the diagonal. Okay, 4 minus 2 is 2. 1 minus 2 is a negative 1. And 8 minus 2 is 6. Fill in the rest with what they were because they don't make any changes when you subtract on the diagonal. And notice I have 3 identical rows here. Okay, so this would quickly row reduce to 2, negative 1, 6 with all zeros for the second and third rows. Okay. Now, you can go ahead and scale if you so choose. Okay, it's a good choice. Nothing wrong with that. So let's divide everything by 2. I'm going to get 1, negative a half, and 3. All zeros everywhere else. And remember, this is augmented with zeros. So I'm going to have x1 is equal to 1/2 x2. Again, it's like it's moved to the other side of the equal sign. Minus 3x3, where x2 and x3 free. So I actually have 2 vectors here because I have an x2 vector and an x3 vector. Okay, so my eigenspace with respect to 2, the eigenvalue of 2, okay, that's what we put in there, would be the span, okay, of a vector here for x2. Okay, so that would be 1/2, 1 and 0. And the second one would be negative 3, 0, and 1. Okay, now you will frequently see, as we've done already in this section, the fractions gotten rid of. So instead of 1/2, 1, 0, you might see them multiply everything by 2, and you would go to 1, 2, 0. Okay, very possible as well. Okay, either of these are acceptable. Those are the same space. Remember, this would be a plane in R3, right? 2 vectors that are independent, span a plane. They're in R3, so it's not all of R3 because I would need 3 vectors for that. So here I have an eigenvalue 2 that corresponds to 2 different eigenvectors. Okay? All right. We're going to have a couple of theorems here. One is going to make our life much easier for some matrices. Okay? What that theorem says, this is going to be theorem 1 of chapter 5. Says the eigenvalues of a triangular matrix are the entries on the main diagonal. The eigenvalues of a triangular matrix are the entries on the main diagonal. Okay? So let's think about why this is the case. So I'm going to take a nice simple 3 by 3 matrix here, and I'm going to make it diagonal. Or not diagonal, I'm going to make it triangular, upper triangular. So nice simple setup. Okay, I put ABC on my diagonal, and then I use D1, D2, and D3 for the others because they're not going to be quite as important. Okay, and so as I look at this, right now, I have 3 pivots. And if I have 3 pivots, I have no free variables. Okay? So as long as A, B, or C are not 0, I have 3 pivots and no free variables. Okay? Well, the easiest way would be to take my matrix A here, subtract little a times I. Okay, so this would give me A minus A would be 0. On the diagonal, I would have B minus A and C minus A. D1, D2, and D3 would not change, and then my zeros below would not change. Now I have a free variable. So that means I have an eigenvector. Okay, 2 pivots, right? B minus A and C minus A. So I would have 1 free variable. And A is an eigenvalue. Because if you have non-trivial solutions, little a then would be your eigenvalue, and you repeat the same thing then for B. So I would have A minus B, 0, and C would give me a free variable, and do the same thing for C. A minus C, B minus C, 0, and that would give me a free variable. Okay, because I would not have a pivot there or there depending on which one I subtracted. So if I'm looking at this triangular matrix, and I repeat this for B and C, repeat for B, C, then A, B, C are the eigenvalues, which are exactly the values that are on the diagonal. Okay, so I can take a really easy matrix here. Let's make my matrix A 3, -1, 2, 0, 4, 1, 0, 0, 2. Okay, my eigenvalues are 2, 3, and 4. So lambda equals 2, 3, and 4. And I could go in and I could do A minus lambda I, so A minus 2I, and row reduce it. I could do A minus 3I, row reduce it, and A minus 4I, and row reduce it. And that would give me my corresponding eigenvectors. Okay? Now notice, if I make one of my diagonal spots 0, so say I go 3, -1, 2, 0, 0, 1, 0, 0, 2. Now my entries on the diagonal are 3, 0, and 2. This matrix only has 2 pivots. So this has a non-trivial solution already, which means 0 is an eigenvector. Okay? Eigenvalue, I should say. So 0 can only be an eigenvalue if you have non-trivial solutions to the original equation AX equals 0. Okay? So lambda equals 0 is only an eigenvalue, if AX equals 0 has non-trivial solutions. And that fits right in with the definitions we've already given to this point for non-trivial solutions, for all of the things we've talked about up to this point. Okay? So if you're given a eigenvalue that's possible, you do A minus lambda I, row reduce it. That'll help you find the vectors. You're given an eigenvector, you multiply A times the vector, and that will determine if that is a multiple. Okay? All right. Okay, so I said there were 2 theorems, so that was theorem 1. So we're going to go to theorem 2 now. And I've touched on the gist of theorem 2 as we were going along here, but we're going to write it down as a theorem now. So if V1 through Vn are eigenvectors, with corresponding eigenvalues lambda 1 through lambda n, then V1 through Vn are linearly independent. Okay, So all of the eigenvectors have to be independent of one another. Okay, because if they're not, then they're just multiples. And as we've seen, I can get different eigenvectors just by multiplying. Okay, you look back at that last one we talked about, right, where I said we could use 1/2, 1, 0, or 1, 2, 0. These are just multiples of each other. Okay, but they're independent of the other eigenvector. Okay, so you can only have then as many eigenvectors, which by necessity are independent, as you do dimensions in your matrix. Okay, so I only have n columns. That's going to be my eigenvectors. That's going to be how many eigenvectors I can have at most. Okay, you cannot have more than that, or they would have to be dependent. Okay, so that dimension n, remember that eigenvectors and eigenvalues only go with square matrices n by n, is very important for determining what you have. Okay. Now, one thing you might be asked to do is to compute an eigenvalue without computation, or an eigenvector without computation. Okay. And so when that would happen is if you have a really straightforward matrix. Let's say I have the matrix 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. These columns are clearly dependent. And if your columns are dependent, that means that lambda equals 0 is an eigenvalue. Okay, you don't have to do anything additional. Okay, I could quickly row reduce this to 1, 2, 3, so it would require some computation. Okay, I could do just no computations at all, which would give me that x1 is equal to negative 2x2 minus 3x3. And so I could write my eigenvectors as being negative 2, 1, 0, and negative 3, 0, 1. Okay, because remember, x2 would be free, x3 would be free in the second vector. Okay. Now, an important thing to notice here that I haven't pointed out specifically, but needs to be noted: the eigenvectors, we use this reduced matrix. Okay. But the eigenvalues do not come from this. So notice this is a triangular matrix. Okay. So you might say, oh, 0, 0, and 1 are my eigenvalues. But look back at some of our previous examples. Okay. If I row reduce a minus lambda I here, say I take a minus 2i, okay? So I'm going to, a minus 2i then would be 3, negative 1, 2. And this is just the one right before theorem 2, if you're looking back at your notes. So 0, I need to subtract 2, sorry. So I'm going to get 1, 2, 1, and 0, 0, 0, okay? That's 1. So notice here the diagonal has 1, 2, and 0. Those are not the eigenvalues. The eigenvalues are 2, 3, and 4 back here, 3, 4, 2. Okay, so you cannot use this reduced matrix to find the eigenvalues. Only the original matrix can you just say, oh, it's diagonal, those are the eigenvalues. Okay, so you do have to be careful. The reduced matrix does not usually, there are some times it does by coincidence, but the reduced matrix does not usually give you the eigenvalues. Only in some very specific circumstances might that happen. Okay. All right. So I have one more example here where we think a little bit abstractly about some of these definitions we've had so far. Okay. So if I have x, an eigenvector of a unknown matrix A with eigenvalue lambda. Okay. What is the eigenvalue of A cubed? Okay. So first let's talk about A squared. Okay. A squared x would have to equal A times AX. Okay, because A squared is A times A. And we know matrix multiplication is associative, so I can do A times X. And I know then that A times X is lambda times x because x is an eigenvector of A with eigenvalue lambda. Okay, I can take a scalar then and pull it out front, so I get lambda times AX. Remember, scalars, you can always come to the front. You can always do associative properties there. Well, AX is lambda x again. So what have I found? I've found that this is lambda squared x. So the eigenvalue of A squared is lambda squared. Similarly, if I go to A cubed, this would be A times A squared x. A squared x, I know, is lambda squared x. Lambda squared is a constant, so I can pull it out to the front. Okay, AX again is lambda x. So this is lambda cubed x. So if I apply powers to matrices, I can apply those same powers to the eigenvalues and find the corresponding eigenvalues for the new matrix. Okay. So if I have A at eigenvalue lambda, then I go to A cubed, the eigenvalue is lambda cubed. If I have A n, it has eigenvalue lambda n, lambda to the n power. Okay. So that's 5.1. Okay, it talks about eigenvalues and eigenvectors. In 5.2, we're going to look at another strategy for finding eigenvalues and eigenvectors called the characteristic equation. Okay, we've done some things to hint at what the characteristic equation might be, but we'll explain that in greater detail when we talk about it in 5.2. Okay, again, as usual, be mindful that you are staying up to date with quizzes, homeworks, checks for understanding, etc. And please let me know if I can be of assistance, and I will talk to you soon, or I will see you in the 5.2 video.